Hello everyone, welcome back to the channel. As promised in my previous video, today we will be discussing computational complexity and how to measure it using big O notation. We briefly touched on this topic before, but now we will delve deeper into it. So what is computational complexity? Essentially, it's a measure of the resources, mainly time and space, that an algorithm consumes during execution. Before writing any code, computer scientists use mathematical tools to predict how fast an algorithm will run and how much memory it will require. This type of analysis is essential for choosing the most efficient solution to a given problem. Now, how do we measure this complexity? The answer lies in big O notation. It is one of the most fundamental tools in computer science used to analyze the efficiency of algorithms. Big O notation mathematically describes the limiting behavior of a function as the input size approaches infinity. In simpler terms, it helps us understand how an algorithm's performance scales as this input size grows. The term big O comes from the German word Ordnung, which means order, signifying the order of growth of an algorithm. There are various types of big O functions, but in this video, we will focus on two of the most common ones: constant time O of 1 and linear time O of n. The more complex notations, such as those for quicksort and binary search, will be explained in future videos. To measure big O notation, there are 5 general steps to follow. 1. Break down your algorithm into individual operations. 2. Determine the big O of each operation. 3. Sum the big O values. 4. Eliminate constants. 5. Identify the highest order term. However, don't worry if I haven't covered all of these steps in detail yet. We will explore more examples and complex cases in future videos. Let's start with constant time, O of 1. Algorithms with constant time complexity have the following characteristics. The execution time remains the same regardless of the input size. The time complexity is fixed and does not increase as the input grows. Common examples of O of n operations include retrieving an item by index or key, assigning a value to a variable, performing basic arithmetic operations, running simple comparison tests. For instance, the operation return data index 0 will always take the same amount of time, no matter how large the data set is. Similarly, using print or console.log always runs in constant time. Now let's move on to linear time, O of n. Algorithms with linear time complexity have execution times that increases proportionally with the size of the input data. If you have 100 items in a list, it will take 100 operations to process them. Key features of linear time algorithms include the number of operations scales directly with the input size. Common examples of O of n operations are copying, inserting, deleting, or iterating through elements in an array. For example, a for loop that processes every element of an array is a classic example of linear time complexity. As the size of the array grows, the time required increases at the same rate. Here are 2 examples to illustrate this. For print hello world, the memory requirement doesn't change regardless of the input size. But in this case, as the input grows, the space needed to store the list also grows proportionally, leading to O of n space complexity. To wrap things up, big O notation is crucial for understanding both time and space complexity in algorithms. Although I didn't cover all the steps for calculating big O in this video, don't worry, in upcoming videos, I will walk you through more examples and more advanced topics. Today's video was meant to introduce you to the basics. More exciting content is on the way, and I will see you in the next video.